This is a macro-level view of a modern cyber-physical grid, defined by sprawling power lines and high-frequency data streams. For a decade, efforts to manage these grids focused on a single engineering question: how to extract enough edge data to be useful without violating privacy laws. This created a conflict between two requirements. Maintaining a stable grid requires high-fidelity data from individual nodes, yet protecting the user requires that those nodes remain private. Treating privacy as a compliance layer added after data has already been harvested has proven to be an architectural failure. These two models represent opposing ways to solve the grid crisis. On the left, the legacy extraction model. On the right, the P3C engineering standard. The legacy model is optimized to pull raw data out of the local environment and centralize it for analysis. This design necessitates the creation of large-scale data lakes, which concentrate risk and create a single point of failure for millions of users. Moving this volume of raw data from the edge to the center creates significant latency and consumes vast amounts of network bandwidth. P3C replaces this extraction process with three strict hardware constraints: equity, inclusion, and diversity. In this architecture, these are not social policies, but technical requirements. They dictate the system must include every node and treat them with equal privacy by default. Meeting these requirements forces the network to use decentralized pathways, where data is processed locally rather than being sent through a central pipeline. Our objective is to map a network topology that can enforce these privacy constraints at scale. True technical equity requires a system where the raw data never leaves its point of origin. To generate truly unbiased intelligence, we have to stop extracting data and start processing it exactly where it lives. Within the P3C environment, we begin with a blueprint of the physical grid. If we zoom in on the transmission web, we can isolate a single glowing origin node. This is the base unit of the network. To achieve absolute inclusion, the system must be able to query this specific node to understand the state of the neighborhood. To achieve absolute equity, the system must do this without ever reading or storing the citizen's raw data. These two requirements create a structural conflict that traditional centralized systems cannot resolve. Traditional networks rely on a sprawling corporate firewall to protect the data they have already collected. The solution is the reversal of Layer 2, which changes the location of the security perimeter. We eliminate the central firewall. Instead, the security perimeter shrinks down, wrapping tightly around a 5-mile radius on the substation map. An authorized local processor is then anchored directly to the substation node, moving the computational power to the very edge of the network. This processor calculates localized ground truth, metrics like voltage stability and load variance, entirely within its own 5-mile boundary. By calculating at the neighborhood level, the system captures a more accurate picture of the grid's physical state. This structure isolates the raw data from the broader internet. Deploying these local firewalls across the grid ensures that no single breach can compromise the entire system. The result is a topology where raw intelligence remains within its own geographic sovereignty. Inside the processor, the physical hardware operates through a continuous series of intense blue energy pulses, representing active computation. A local firewall is only effective if the raw data it processes is immediately destroyed. This interface shows the ephemeral computation sequence. The command gc.collect runs alongside the blocks of data stored in active RAM. The processor executes garbage collection, and the raw data blocks instantly evaporate from the memory. By clearing the RAM immediately, the system ensures that raw data is never written to a hard drive or persistent storage. Standard encryption leaves a scrambled file on the disk that could be targeted later. This method removes the data from the physical hardware entirely. This makes data extraction a physical impossibility. The material required for a breach no longer exists. It is a fail-safe that protects the system from both external hacks and internal data misuse. Privacy is enforced by the physical clearing of the memory cache, which removes the possibility of a data leak. Once the raw data is destroyed, only one artifact remains. A single cryptographic key generates and locks into place. This is the only information the processor will output. This is a cryptographic attestation, a simple proof that the local grid data was verified. Unlike raw data packets, this key contains no personal information and uses very little bandwidth. The system validates the state of the neighborhood without ever transmitting the underlying memory of the citizen. If we pull back from the microchip to the multi-state grid, we see how these local signals integrate into the wider network. The local attestations are now ready for macro network transmission. This map shows thousands of individual attestations lighting up simultaneously across the region. The discrete pulses blend together, forming a unified baseline of the grid's health. The massive volume of these continuous transmissions creates an additional layer of anonymity. Security is reinforced by the sheer scale of the cryptographic output. An individual node's signal becomes indistinguishable when mixed with millions of other attestations. The density of the network acts as the final barrier against identification or surveillance. This illustrates the core principle of the architecture. The mass hides the local. This keeps the system safe because only the verified proofs, and never the raw data, are moving across the grid. By combining edge constraints, fast ephemeral processing, and mass-scale cryptography, we create a new type of network. This engineering sequence allows us to generate multi-sovereign intelligence. The future of these systems depends on shifting away from data collection and toward hardware-guaranteed equity.